So multimodal models are really an important way for us to mimic humans. Humans reason in terms of not just a single modality like text. Rather, we have complex sensory inputs that involve seeing, hearing, smelling, touch, in being able to incorporate all of these sensory inputs as an input to the brain for us to reason and act in ways that make them appear as intelligent and be able to achieve things that is not possible by most of the other organisms in the world. So, I mean, one of the ways the science and language models has been progressing is thinking in terms of ways that human brains have evolved. So the research community believes that this is an important step towards achieving AGI, artificial general intelligence. Our model should be able to process not just single modality, but really process multiple modalities, just like how humans do, and enable to effectively make sense of the world around us, the complexities that involve around us. And this could be, just to give an example for where this could be helpful, for instance, if you have access to the audio, you could maybe infer something about the environment. Maybe you're in a place where there is flight movement and you're able to hear them loud because you seem to be closer to an airport. And let's say you are able to see some images that talk about a greeneries. You could infer that to be a park that you're probably seated. So understanding the context in terms of where you are and what surrounding characteristics look like, that would help us to reason you better. Like, for instance, if there is a situation that arises where you want to take a decision, having these contextual inputs where you are helps in refining the best next possible action that you could take in order to make a decision. Right? So that's a bit of a motivation. And then we could talk a bit about how we can classify multimodal models on different dimensions. So multimodal models, and so this is a rough pictorial about how we can think about some of the ways to classify or categorize multimodal models. And so one of the obvious one is depending on the modality in terms of understanding what kind of modalities are supported, which could be text, images, videos, touch, and other digital sensory inputs. And the other one might be in terms of it's, if you were to think of this in terms of a system behavior, what are the inputs and outputs supported? Not every model supports all modalities in both input and output. And I wanted to motivate this with a human analogy, where if we think of our multimodal models as equivalent of human brain, then we can think about what are the inputs and outputs to this as a system, and we'll start to see we can start to see some of the patterns there. For instance, inputs in our world are really sensors, in the digital world, I mean, and output in our case could be actuators. These are things that we do in order to influence the state of the world, the state of the environment. It changes the characteristics of the environment. So when we think about, again, sensors, we can broadly think of this as ability to see, hear, smell, touch, right? And each of these have parallel correspondence. For instance, seeing is in terms of the digital perception, it's possible through images and videos. Hearing is through audio. Smell is still very exploratory, but there are some advances being made, with some startups working especially in terms of trying to understand how can we digitally sense smell and actually actuate them. Touch, again, this can be in the form of click maps, XY coordinates, or other ways to represent where the user is touching on a given screen. So all of this again becomes applicable in the output space, which could be actuations, where you could think of this as speaking out, draw or paint, right? And the speaking would be again equivalent in terms of audio outputs. This could be image or video outputs, right? So when we think about multimodal models, this is another way to think about it. And since we're talking about audio language models, we could have models that can process audio, that can process text, but then there could be few models which can process both audio and text in a single step. Similarly, on the output side again, we can think of audio plus text, and this could be roughly equivalent to speaking. This could be roughly equivalent to just writing. And similarly, when on the input side, this could be about hearing and reading, right? So today, most of the models that we talk about that's available to us, both proprietary and open source, they work mostly on the perception side, where the modalities are being enhanced on the input side. But most of the existing models focus on text-based output modalities. So because this itself is a huge leap, if you were able to understand and make sense of the world in a multidimensional way, incorporating different sensory inputs like images, videos, and text, that in itself is a big leap in terms of being able to make sense of the world around us. And now there are the next step could be you might want to enhance this with more advanced things, like for example robotic arms, where you could actually, let's say, move things in the physical world in the form of let's say motor skills, motor-based actions, and so on. So those are all some of the things that are currently happening as well. There are a few startups working on this space about how do you use these large language models, primarily the multimodal models, to be able to influence the world in the form of physical outputs, where you kind of move things, organize things around, and so on. But in the realm of, again, audio language models, like I said, most of the models talk about audio and text as input modalities, and there are a few models that are starting to output speech, text, and combined speech and text. One of the notable open source models that's available for us is qwen-audio, and this is a good model that is trying to do a bit of both, trying to understand and make sense of audio and text and bring it into a unified stack for us to use them. So this is an example of a multimodal architecture that's becoming more common these days. And in this particular one, I've taken inspiration from a couple of papers from the audio domain. These are AudioPaLM, SpeechGPT, LTM. There is also AudioPaLM and qwen-audio. So these all have used similar architectures with some minor modifications to this in order to represent multimodal audio models. So at the heart of these model architectures is basically one of the common themes that we're seeing is increasingly using a large language model. Let me get to pen. So one of the common themes that we are seeing is most of these efforts start with a strong LLM, which is being trained on text-only data as a backbone for building multimodal models. AudioPaLM from Google, they use PaLM 2, which is a 500 billion plus parameter model. Similarly, qwen-audio uses qwen-LM. I don't remember the size, but again, they are again large language models with big parameter counts. So often the starting point is bootstrapping it through one of the large language models that are available in-house to extend or build multimodal models. And by freezing the large language model itself, one of the ways that people build models is to, one way to think about this is to expand the vocabulary of this LLM with text tokens into what is called as audio tokens. And maybe we can spend some time on what audio and text tokens are. So when we think about text, I think it's a well understood domain. For example, if you have the word complexion as a word. These are discrete spaces where you can actually think about how do you break this into tokens that can be then utilized for the modeling purpose. Like one way to think about this is in subwords, where most of the modern tokenizers, they would likely split this into complex. Complexion might be split into two tokens. And these are text tokens. And then each token itself might have a ID associated with it, let's say 13, 15. And so really this would become the problem of how do you tokenize this would be in like two particular tokens. So you could basically approach words by using subwords, sentences using, again, subtokens or subwords as you call it. And in this case, this is one way to tokenize. And this is the basic idea behind tokenization is how could you reduce it into a small set of units that are that can give compressed representation of the input modality, and this becomes a representation for the large language models to learn and basically produce these in the outputs as well. So this is a very known thing because it's text, it's discrete. We have very clear ways to tokenize. But we look at audio again now. We have this problem of how do you tokenize, or how do you break this down into smaller components, which can be used in the LLM space. And when we think about this, there are a couple of different ways that the researchers have approached. Like one way to think about this, and this is not just in this space, but this has been the norm, where you could split the audio waveform into multiple frames, as it is called, and each one could be lasting a couple of seconds. And in this case, we have a 25 millisecond frame. So this becomes an input that we want to tokenize, let's say. So we could think about this as a way to extract features as 25 millisecond frame, and you can have this as a moving sliding window where you keep doing this for every consecutive frame. And this itself can be represented in the form of a frame embedding. And there are different architecture representation learning frameworks like Wave2Vec, there is Hubert, and a couple of other things. I think Google has USM. All of these are basically different ways to represent this 25 millisecond frame in the form of an audio embedding. And now, one of the common ways to further create what is called as tokens is to take these embeddings in whatever n-dimensional space. I'm projecting it into a two-dimensional space for simplicity. Let's say we have a few points that are really clustering together, and we can choose this cluster value. Let's say we want to choose 50 clusters. We can then start to project each of these frame embeddings into the nearest cluster means and start assigning tokens. So now based on this, you could start to assign tokens. Let's assume your text vocabulary is 30K. Now you can really start to give different token IDs to this. It could be 1, it could be 17, 31, and whatnot. So this becomes an extension of your text vocabulary. And now, just like you're encoding this text where you are saying different IDs 13 and 15, now you could start to do the same thing here, where this could be 1, 7, 31, and so on. So this becomes your audio tokens and text tokens. The joint vocabulary would be basically a combination of text and audio tokens. And you would basically train this neural network, not usually from scratch. Like I said, you would bootstrap with one of your strong LLMs, but you would additionally want to freeze some layers, maybe fine tune some of the layers with additional multimodal data. And this could be through self-supervised learning or objectives and supervised objectives as well, which includes both modalities. For example, audio captioning is one where you could ask to caption an audio which involves text. So that's a joint space. Or audio question answering, where you could have an audio and a question and try to ask what's in the audio, or you could ask it to do transcription, translation, and whatnot. All of that becomes a way to learn the joint representation or refine the joint representation. And in all of these tasks, the bootstrap model helps in the accuracy of audio tasks. And there has been qwen-audio people talks about how the large language model helps to improve the accuracy of ASR and translation related tasks. So the LLM is really not bringing the world model from a text perspective, but it's also enhancing with audio related tasks when you're doing one of these training with these tasks. So so once the multimodal data is used for training, we could think of this LLM, and most of these LLMs are autoregressive decoder-only models. And that has become the norm in terms of the research community adopting this architecture. And we can think of this as now the model autoregressively generating tokens. So we could have interleaved text and audio tokens coming out. Like in this case, there are audio tokens that are being split out along with some text tokens, because in this question we have asked to respond by the sentiment in the form of text, but respond in the form of audio. So you can see the output of this model is really a combination of both, and this itself could be again different tokens which get de-tokenized. In this case, you would de-tokenize using the same tokenizer that you used for tokenizing the inputs to get back the actual output from the model. And in case of audio, you have another additional step, because the output of de-tokenizing an audio is still an embedding. So you need some way to go back to a spectrogram, and which is usually done through a vocoder or what is called as voice decoder. To actually reconstruct or construct a spectrogram which can then be played back on a device. So this is mostly the high level details around multimodal architectures and how they are evolving from LLM as a backbone, as a backbone in most of these cases. So AudioPaLM is one of the early papers that really started audio language modeling, or what's called as multimodal models. So the idea is very simple. This was a paper from Google back in 2023. And I believe they had an earlier version of the paper sometime in 2022 as well. But the idea was basically a simple one. Google was already working on developing large language models like Palm. They had Palm 2, Palm 1, Palm 2, and especially for this paper, authors from Google, they test using a language model. It's Palm 2, and I think it's about 500 plus billion parameters. And they try to give audio capabilities as input to this particular model to see how it can generalize to understanding from just text domain to understanding audio domain. And this was an interesting idea. So Palm is Palm. So as it says, it fuses text-based and speech-based language models. Particularly, they talk about fusing Palm and AudioLM, which was another work from 2022. And in this particular paper, they talk about a couple of novel things. One is, like I said, in terms of the multimodal architecture I discussed, they try to expand or do a joint vocabulary learning by extending the text tokens to build what is called as audio tokens, and then use that joint vocabulary to train this model on joint text audio tasks. And I'll talk about what tasks it really cater to. And until this point, most of the models were concerned towards ASR, TTS, translation. Each of these were research domains in itself, and they had their own models and architecture, whatnot, which focused on each of these different tasks as not necessarily related. But this was one of the early papers which started to see all of these tasks to be unified into a single model. So they in this case they talk about 4 different tasks: speech recognition, speech translation, speech to speech translation, and I believe text to speech is also one of the other capabilities, but I can confirm. So this was a novel idea about doing a multitask learning that caters to 4 different mainstream use cases for audio. And yeah, there's some good introduction about multimodal models, what their thinking is behind this particular approach. And particularly from image, they talk about this model called Flamingo, which I believe some of you might have heard about, especially working in computer vision domain. And in this case, this was one of their motivations to sort of bring this for audio and speech-to-speech translation. Yeah, so one particular note about speech-to-speech translation, again, until this point, most of the field was concerned when we talk about speech-to-speech translation, they would think of this as a cascaded model. Any applied team would go about trying to recognize the text in a particular language, and then convert them into a different language using text-only model, and then talk back to the user in a different language using a TTS model. So this was obviously not optimized end to end. So there were definitely losses as one moved from model A to B to C. And this was one of the early models that tried unifying all of these modalities into a speech-to-speech modality, which means this is not just multimodal in the input space, but it's also multimodal in the output space. Yeah, I think this is a good illustration for what they're talking about in terms of their architecture. So you can see there are some tokens, S2S, French, English, and that becomes the prompt, which is the text prompt. And then you can see there is this waveform itself, which is the audio. And you can see the green and the blue ones. They are used to denote the audio tokens and the text tokens. And as you can see, there is text embedding matrix, decoder and transformer. So these are basically initialized from the PaLM 2 model. And this is kept frozen. And they also introduce what is called as audio embedding matrix, which basically takes care of audio tokens and then helps build a joint representation for the decoder only transformer to act on. And then, as you can see again, the output can be a mix of audio tokens and text tokens. And in case of audio, these tokens are again passed through a vocoder like SoundStorm or AudioLM to eventually convert back to a spectrogram. And when it is text, it's detokenized using the text PaLM detokenizer, and you get back the text. Like in this case, you're asking for recognizing the speech, which is in Italian, and you actually see the transcription. So if you remember, if you see this, you might recollect how T5 was trained. This brings some aspects of T5 prompt-based or prompt or instruction-based audio models, you can say, to some extent. I think it reminds T5 to some extent. And of course, there's some good text about how do they plan to expand the token, how do they plan to expand the tokens, the audio tokens, and a couple of different techniques they talk about, including word-to-vec or wave-to-vec, and then trying to do a clustering on top of that, which is what I think Hubert does. They don't specifically talk about Hubert, but I think this particular paper implements wave-to-vec BERT and does quantization on top of that to get audio tokens. And yes, I think that's for the most part. And there are some, like I said, these are the prompts that are used for representing the task itself. Training, make sure they talk about what data sets are used for pre-training. And then there are some interesting metrics that they compare even the state-of-the-art model like Whisper and how it performs better than that. And they talk about speech recognition and speech translation, all of this getting benefit from the fact that they're like bootstrapping with a really large language model that's learned that has been trained on the internet corpus of text. So they seem to talk about this helping them in improving the accuracy of the speech translation. So similarly, there are metrics for ASR, and they pretty much show it beats multiple benchmarks for both ASR, AST, speech-to-speech translation. And then I had 2 other papers to talk about. SpeechGPT, I'll not go too much into this, but again, this is a multimodal audio model, which is again using the same idea of trying to use text and audio as input modalities and trying to output text or audio in the output modalities. Very similar again. I don't want to go into the details, but you can look at this the architecture. It has many similar components here. In this case, they don't bootstrap the language model, rather they use or they pre-train the language model from scratch by using self-supervised learning and supervised learning. I think one novel contribution that this paper talks about is in terms of what is called as chain of modality instruction. This is something that you can think of as a parallel to chain of thought. If you are asking to do a speech-to-speech translation, you could rather ask the model to break it down into simpler tasks. For example, you could still ask the same model to generate transcription and then do the conversion. That improves the accuracy. So this is what they call it as chain of modality instruction tuning. And this is one of the novel contribution. And then they use a bunch of synthetic data to train this whole speech to speech GPT. Again, interest of time, we can maybe move on to this particular model, which I'm very excited about. It is a fully open source model from Alibaba. And I believe this is one of what we can call as an audio foundation model. As you might now be aware of the term foundation model or world model to mean something that models the world knowledge about a particular topic or domain. In this case, I believe qwen-audio is really means that foundation model for audio, because they also talk about universal audio understanding. And they really take this to 30 plus tasks in audio and speech domain, which is a lot. So that includes all the major use cases like recognition, translation, text to speech, maybe not text to speech, recognition, translation, understanding, captioning, and a bunch of other things that speaker identification and so on. So they released two models. One is called as qwen-audio and qwen-audio-chat. This again uses a similar architecture where there is an LLM that is being enhanced with an audio encoder as an additional input to the autoregressive transformer. So there's some good information about the intuition behind modeling this as a universal model. As you can see, these are all the tasks they cater to. Each of these are like different audio data sets. It could be audio classification, speech captioning, sound classification, and a bunch of other things. So I'll not go into, again, too much of details. Maybe we can look into the architecture and a few examples. Like as you can see here, again, they're using an instruction-based paradigm where there is an instruction which is in the text, and then there is an audio. So this would be trained on interleaved audio text. And they typically talk about this as this is a speech recognition task. And this is interesting. They talk about using multiple audio files and trying to do some kind of a audio analysis task to understand who is talking or if audio 1 and audio 2 are related and so on. I have some very cool tasks like audio reasoning. These are very interesting and sort of next, I would say, next step in the frontier of audio models, where just based on audio, you're trying to make sense of where the user is and what the environment conditions look like without having any other supervision about the domain or the environment characteristics. And maybe we can go to the architecture. Yeah, this is the architecture for qwen-audio. And just like AudioPaLM, which was based on PaLM as the language model, here they use qwen-LM. This is a large language model that Qwen has released, which is trained on, again, very similar techniques like how PaLM is trained on. And in this case, they use Whisper as the audio encoder, and you can see that there is this audio tokens that they are generating based on the audio encoder here. In this case, the way they prompt this model is slightly different. They make use of the Whisper's transcription tags, and they particularly talk about an innovation where they talk about hierarchical transcription tags to be used as a way to avoid interference between different tasks and preserve the accuracy of individual tasks itself. but otherwise it's a very similar architecture. The only difference here is, in this case, the output is only confined to the text domain. They don't really do text to speech or speech to speech. So audio is not in part of the output domain. Maybe we can soon expect one which is also doing audio outputs. But for now, qwen-audio-chat is going to be audio plus text in the input domain and text in the output domain. So another very cool examples. I'll not go into that just to keep the length of the video short and not bore you with details. But yeah, there are some metrics with respect to how there's one particular task which they call SRWT, which is timestamp detection, speech recognition with timestamp, and they talk about how this timestamping itself helps in improving the accuracy of ASR task.